In this talk, I'm dealing with the morphology dynamics of migrating immune cells, especially neutrophil leukocytes, which crawl under interaction with varying surface geometry and mechanics. Using nanopatterned elastomer substrates and real-time single-cell monitoring, we'll see how anisotropic surface guides neutrophil alignment, elongation, and movement during crawling. Neutrophils are the most abundant type of leukocytes and the fastest cells in the body. In the bone marrow, they are differentiated from progenitor cells to mature neutrophils, then circulate through the blood vessels. When the neutrophils detect chemoattractant released from pathogens, they adhere to the endothelial lining and migrate towards the pathogens in a 2D and/or 3D manner. During crawling, it is well known that the mechanical coupling between the substrate and intracellular actin fibers could dictate the neutrophil's morphodynamics. The cells adjust their shape and motility via dynamic reorganization of actin architectures according to the elasticity or viscoelasticity of surface. In order to induce the neutrophil adhesion, spreading, and crawling, the specific signaling pathways in the cell should be activated by chemoattractant molecules such as FMLP. Being in a spherical shape in a suspension, the neutrophil adhesion kinetics evolves to the addition of FMLP with deviation from the initial round shape with time. Furthermore, it has been demonstrated that the neutrophil shape change, together with the cell dislocation, can be triggered in a uniform concentration or in a gradient concentration of FMLP. In another study, the neutrophil spreading area was shown to be dependent on the substrate elasticity, where the spreading becomes firmer with increasing Young's modulus in the range of 5 to 50 kilopascals. In addition, the migratory behavior turns out to be more persistent with higher substrate elasticity, as is indicated in the crawling trajectories patterns. And otherwise, the crawling speed is decreasing with increasing stiffness from 10 to 100 kilopascals. On the other hand, neutrophils have long been known to exhibit contact guidance in response to the surface topography. When the cells are incubated and activated on a gel surface of aligned collagen fibers, each crawling trajectory appears to be roughly parallel to the surface anisotropy. Based on these backgrounds, we aim to investigate combined effects of substrate topography and elasticity to migratory behavior of cells and the morphology-motility relationship during 2D crawling. We utilize elastic substrates fabricated using polymer elastomers with nanopatterning for creating parallel grooves on it. And we use primary neutrophils isolated from murine bone marrow, incubated for 2 hours to allow the settlement and adherence on the substrate. And then we add chemoattractant FMLP and perform time-lapse phase contrast microscopy. So, activated by a uniform bath of FMLP, neutrophils show guided polarization and migration behaviors along the surface microgrooves. And using image analysis, each cell edge is detected as a time series, and various morphology and motility features are extracted numerically. In this example, we find that the cell elongation indicated as the aspect ratio is strongly associated with 2D shape isotropy, represented as the circularity, as well as with the non-convexity of the 2D morphology, which is parameterized by solidity. Here, the solidity is defined as the ratio between 2D cell area and its convex hull area, so that lower solidity value is interpreted as higher cell membrane deformability. When you repeat this experiment for many neutrophils by testing 4 different combinations of 2 topographic conditions, patterned and flat, and 2 different elasticity, 2.5 gigapascals and 6.7 megapascals, it appears that the cell speed during crawling has a little difference in all combinations of substrate topography and elasticity. On the other hand, if you analyze the cell polarization angles to the direction of substrate patterns, we find that stronger surface compliance induces higher degree of cell alignment to the pattern orientation. In a similar way, we can plot the cell polarity for different conditions of surface topography and elasticity. First, in this graph, it is found that the crawling neutrophils are more polarized or elongated on the grooved surface and on the stiffer substrate. Next, in this graph, if the aspect ratio is plotted as a function of centroid speed, it appears that the cell polarization is positively correlated to the crawling speed, particularly for the pattern surfaces. More specifically, the correlation between polarization and speed is stronger in the order of stiff patterned, soft patterned, stiff flat, and soft flat substrates. Now, when we focus on the neutrophil circularity as a measure of 2D cell shape isotropy, we see that the plot of circularity versus centroid speed indicates that the both variables have strong negative correlations in the order of soft patterned, stiff patterned, stiff flat, and soft flat substrate, so that the topography is more critical factor in determining 2D cell shape isotropy. Finally, the concave local shape deformation of cells parameterized by 2D solidity is found to develop more prominently on the grooves and stiffer surfaces. That means crawling neutrophils exhibit higher deformability, that means smaller solidity values, on the patterned and stiffer substrates. Then, if we plot the solidity values against centroid speed, we find again negative correlations between the both variables, showing that the degree of correlation is higher in the same order to the previous case of 2D circularity. This implies that the topography, again, is a more critical factor in determining the crawling neutrophil deformability, and probably cell shape isotropy and membrane deformability could be related to each other. In summary, in view of design of structured biointerfaces, there are 2 main messages from this study. Firstly, neutrophil migration speed on the micropatterned surfaces demonstrates stronger correlations to the cell polarization, shape anisotropy, and membrane deformability when compared to the flat surfaces. Secondly, the synergy between surface topography and stiffness may drastically influence the temporal morphology evolution of a migrating neutrophil on a 2D scaffold. One of the future directions of our work would be an investigation on the cell shape translocation relationships through contact guidance and stiffness feedback under in vivo-like shear flows. To achieve this goal, use of microfluidic devices could be the best choice. So currently, we are fabricating microfluidic chips using 3D printing-based molding techniques in order to create topographic patterns on the surface of microchannels with finely tuned substrate elasticity. For the last, I would like to thank my group members, collaborators, and funding sources. Thank you for your attention, and I would be happy to have your questions or comments.